可不可以带那个
小抄？
对，所以我等一下应该还会再发。
可以啊，可以啊，就跟以前一样。哎，好，那就开始了。好，好，谢谢。Good morning. Welcome. Yes, such a heavy rain. Traffic was quite bad. Right. So let's continue our lecture. Oh, by the way, next week we will have our midterm one. Midterm one will be chapter, PDF 1, 2, 3. Okay, review. All right. So yeah, suppose is that 10? I don't know. So actually, just follow PDF. All right, PDF 1, 2, 3. Okay, 1, 2, 3, and we will have some rules that will be announced by teaching assistant in the Facebook or E3. All right. Suppose they will. We will have two classrooms for the examination. All right, so you just follow the instruction, and also, you're allowed to bring a script. All right, the script A4, maybe it's A4. I mean, follow the rule. All right, follow the rule. I forgot what kind of rule I have. Okay, but every year we have the same rule. All right, so don't violate it. All right, so 听得懂吗？就是我们要有第一次期中考试1到3的 PDF。OK， 1到3的 PDF， 然后你可以带小抄，但那个小抄的规则，我有点详细，我有点忘记了哈，应该是 A4 单面吧，我记得是这样。好，不过没关系，就看公告是什么。那公告已经每一年都一样，好，所以就很公平，好，所以不要去违反它。之前有人违反，然后就真的就0分，就拜拜咯。好 ，So there was a senior that violated the rule of the script. All right, so that guy just bye. Okay, cannot pass this course. All right, so yeah, be careful and be prepared. Okay, so let's continue our lecture. Suppose I need to finish most of the part of PDF 5. Okay, PDF 5. So let's continue to finish the chapter 4. Right. So last time we talked about we talked about how we determine the molecular flux, right? Okay, molecular flux. And then we talk about how to determine the molecular speed for the distribution, okay, of the distribution. And we talk about how to find the FV. But before we talk about FV, we talk about capital F because it is related to the direction. It's easier. Okay, it's easier. And then after we're using the direction of the velocity and also the probability of the bumping, and then we comes up that the velocity distribution looks like this form. Okay, so of course, if it looks like this form, the values also looks like that form. All right, and then we're going to determine the A and alpha. And then we found that the exact, the distribution of the velocity, it looks like this. Okay, if you can change in the temperature, it will change the distribution, of course, the shape of distribution. And then once you determine the FV, you can get NV and FV, and then you can get the mean speed, root mean square speed, and most probable speed. And then we introduced 1 degree of freedom only and Vx. All right, and then there's some really essential point that the growing I would say the limitation, the range of the V is different from 3-dimension to 1-dimension. 3-dimension consider a ball growing, so it starts from 0 to infinity. And if you consider 1 degree of freedom, it's a plane moving, so the plane is going from minus infinity to positive infinity. All right. And then we talk about mean free path. And then we also talk about the relative velocity factor. And then we notice that the L is proportional to 1 over P. Okay. And then we show that Y, the square root 2 is the relative velocity factor. And then we talk about probability function Px. We talk about the Px is that particle won't hit any other particles, the probability. All right. So of course, mean free path will be related to this Px. And then we use several math trick, and then we can find Px is also in exponential form. All right. And then we found that the exponential form is actually, we want to find the connection between mean free path, and Px. The Px can be related to probability density function, probability of density function. And using this fx, you can using expected value to get mean free path value. So now we successfully link P and L, and then we found that if you travel the mean free path, actually only 37% won't hit others. All right, which means that 63% particle will bump to others, and then cause they leave the cylinder. All right, if you travel the mean free path distance. And then we talk about the effusion. The effusion is actually a container has really small hole, a small hole that the particle, if it bump to that hole, it can escape from this container. But how small is small? Which means that if your particle travel in distance of the mean free path, and which means that you have 37% stay there, okay? And which means that it typically will survive during that journey within the distance of L. So the L is actually a really good indicator of the scale that is small or big, to see that this is small or big. All right. Then we found that, okay, the L has a travel direction sphere area. Then the area need to be bigger, much bigger than the small hole. Yeah, this kind of makes sense, right? So we're using this relationship and come out, okay, our D need to be less than 0.4 L. And then this hole can be called small. All right. But which means that D is so small that it's really difficult to achieve by human being, right? So what we can do is that if the L is bigger, which means that D is easier for human to achieve. So how can we easier to achieve the D? How to make the L become greater? We can lower the pressure, and then to make the lower the pressure and make the mean free path L become greater. So the D is easier to achieve by human. All right. So effusion is essentially a low pressure phenomena, All right, so let's continue. And then if for ideal gas, we know that, I mean, to find the flux of the D here, we're using this, right? We know this 1/4 N underbar V bar. This is, we showed that in the previous in last week, right? So for ideal gas, the N dash N underbar is N divided by V, all right? And then which is equal to P over KT, right? And also we know that V bar is 8 KT and pi m 1/2. So that make the flux is P over square root 2 pi m KT. Okay, so in the mean for ideal gas, we can find the flux is looks like this, and then we found that the m here is quite crucial because you are saying that, okay, the P here has been lowered by human, that's okay, and the temperature is also fixed in the system. So if you have two things in the container, and which one can go out, escape, and doing the effusion, which one has lower mass. So which means that you have if you have lighter molecular, you will have higher chance of going to the molecular flux to the area, and also you will have higher V bar, right? So you have lighter and faster molecular. If the molecular is lighter, it becomes faster, and it's easier for it to assess that hole, right? So that is useful for the effusion method, was used to separate isotope U235 and U238, and to make the atomic bomb. All right, so I guess I've watched the Oppenheimer movie, right? This is quite a nice movie, and then I watched kind of twice, and I quite like that. And that's the way that they separate the two isotope, and then you can using the effusion to make atomic bomb, right? That's it. 好，那这个是effusion，我不知道怎么翻译哈，就反正就是它就可以有一个超小的洞，然后就会逃出去。那要怎么逃呢？那个洞要很小，而且那个不要去，而且要非常稳定啊，哈，维持稳定。但是又要把东西分离出来，要怎么做呢？那洞要非常小，怎么叫做小呢？就是它的这个平均自由路径的这个运动范围的这个面它是一个代表那个 particle 那个颗粒的运动的状况嘛。它这样子的范围要比你的洞还要大很多，那这样才叫做那个洞很小嘛，对不对哈？那这时候我们就运用了这些技巧，就得到了D 要小于 0.4L。那 L 要怎么样？D 要怎么？那 D 洞很小，那人要怎么去做到呢？所以其实以我们人类的技术来说，当然是希望 L 越大，我们的 D 就可以越大了哈。那 L 要怎么越大呢？就 P 越小就好了。所以说实际上effusion 是一个低压的一个现象，然后我们又知道颗粒要跑出这个洞，表示说你一定要经过它嘛，所以跟那个 flux 有关。那 flux 是这样子写的，那这个 flux 的里面的 n underbar 在 ideal gas 里面是这样子，然后 V bar 是这样子。好，我们就写成得到一个这样的式子。那这是代表什么呢？这代表说，如果你看到这，因为你 P 已经设定了 ，T 也设定了， 如果你今天这个容器里面有2个气体的分子，越小的那个它就会跑越快，然后它也有越高的几率、越高的 flux 在这个洞上，所以它当然就会越容易跑出来。那所以这 effusion 的 method 就可以用来去分离这2个同位素这样子。OK， now next one, mean speed of escaping molecules. All right, so molecules of the number of molecules with speed in the range v to v plus dv, and striking that surface per unit area per unit time. So we are going to find the mean speed of escaping that small hole. All right, so we are going to determine expected value again. Okay, so mean speed of escaping molecules is actually what we determine from here, right? And the NVdV is actually the Maxwell-Boltzmann speed distribution, right? So we are going to do the expected value. So you can see we do the 0 to infinity, 0 velocity to infinity velocity, and times the v. So this is expected value, right? Expected value. And you see how to get that expected value is that the velocity for itself divided by the total velocity integration and times the v here. And then you can find 0 to infinity v4 exponential minus mv square 2kt and dv. And the bottom part is 0 to infinity v3 exponential minus mv square 2kt and dv, which is equal to 0, which appendix, you can use appendix D. I forgot which equation. All right, sorry, but it's not really important. The result is 2 pi kt divided by m 1/2, which is 1.18 v. Okay, what is v? 1.596 kt divided by m, half. All right, so you can see that v bar for escaping is 1.18 mean speed. All right, so if we substitute this here, and then we can find that this is 1.18 times. So you can see that v escape should be greater than mean speed. So which means that it's a little bit more difficult than normal speed. You need to get higher speed to get higher chance to escape. All right. So the faster molecule have greater probability to finding the hole and get escape. Right? Makes sense. 好，这边就继续刚刚的东西哈，就是说我们不是说要用那个 molecular flux， 比如说它要去撞到这个墙嘛，对不对？哈，撞这个小洞嘛。那这个洞要怎么样撞到呢？用什么样的速度去撞到呢？应该说平均的速度，我们想要找到它。好，那这就是 NVdV， 就是用我们之前的 speed distribution 嘛，对不对？哈，那我们把它带进去以后，我们就会发现，就是说我们可以使用 expected value 的方式去看看它的速度跟它的几率。那怎么样几率法呢？就是这个的几率就是除以它全部的就好了哈，它全部的总几率从0积到无穷大，那这样子就是它的 expected value， 叫什么？期望值了嘛哈。所以说我们的 会撞到这个孔，然后它的平均的速度会是多少呢？所以你可以发现，如果我们今天用这样的方法算的话，用 Appendix D，然后我忘记是哪一个方程式，然后 D2 还 D3 我忘记了，还 D1，反正就把它带入进去，然后就可以得到这样的式子。那这样的式子跟 V bar 的差距是 1.18 倍，也就是说，你平均逃出去的速率要比平均的速度还要高 1.18 啊，高一点点，好，你才可以，就等于是说你要跑得比别人快，你才可以有机会找到那个后啊，那其实跟人类的社会也是蛮像的啦哈。好，那基本上就是这样。那第4章就讲到这边。好，等一下就回到第5章。第5章的话就是 Statistical Thermodynamics， 就是统计热力学。好，那就是还蛮全新的一个东西了哈，跟几率非常非常相关。Later we are going to entering chapter 5, PDF 5, statistical thermodynamics. All right, and this is completely new chapter that we are using different point of view, perspective to see the thermodynamics. All right, so get ready. 很可惜的是，就是我的第4章竟然要3次 writing 的 upload 3次答案。Okay, so let's continue to the next. Statistical thermodynamics. Finally, okay, after 2 months, okay, 2 months, and then we finally get here. Statistical thermodynamics. Let's go. Okay, statistical thermodynamics. Finally, we are here. And the history, brief introduction for statistical thermodynamics. Okay, thermodynamics is the study of energy and its transformation. Makes sense. All right. And we consider the progress and classical thermodynamics without taking any atomic theory. It's a whole. Okay, it's a whole. Not whole. It's a whole. I don't know how to say that. Different with a W and no W. But we consider the entire stuff. All right. But offer 0 molecular insight. No molecular insight. Okay. No molecular concept in the classical thermodynamics, but which is not true, right? Everything is combined, composed by molecular. So this is not correct. 0 molecular insight, so which is not really good. So we found that statistical thermodynamics, we developed that to connect microscopic properties to the already well-established macroscopic behavior. All right, so this is quite important that statistical thermodynamics is kind of trying to connect microscopic properties, something related to molecular, okay, molecular, and to connect them and to explain the macroscopic behavior, the behavior that we see in the normal day, in the daily life, okay, in the normal scale, in the human scale. So we observe all these behavior for a long time, but now we are going to use the microscopic property, which is molecular behavior, molecular behavior, to connect them and explain why we will have this behavior. This is quite nice. Okay, so most simply for statistical thermodynamics related to the average. So you can see that many molecules. And how can you conclude one behavior from all the particles, all the molecules, by using average? Okay, of course, there are many ways to average it. So that's how we introduce the method or theory to done this average. So average of a molecular property, which is microscopic property, all right, to bulk thermodynamic property, which means macroscopic behavior. So you can see actually these two sentences are repeating itself. Okay, this one is equal to this one, and that one equal to that one. And the only more information is that how to connect them by using average. All right. And so the objective of statistical thermodynamics is a particle theory. Oh, particle. It's a particle. So that's the reason why we are going to introduce kinetic theory before entering this chapter, because particle all about moving, all about choosing direction or something. So it's all related to kinetic. So that's the reason why we talk about the kinetic particle theory before we actually enter this chapter. And of course, we are going to say the particle theory to interpret the equilibrium properties of the daily life scale. All right， 好，历史讲一下哈，基本上就是我们当然一开始要先讲说啊，这个传统热力学真棒，但是它少了一个没有任何的分子的概念。但是这不是正确的嘛，哈，我们都知道，我们都是用分子组成的，所以呢，统计热力学的意思就是说，我们需要用分子的现象、分子的行为去连接到巨观行为，就是我们平常实验观察到的东西的现象。怎么做呢？做 average， 我们把分子的行为做 average 平均。好，那这个平均有很多种方法，有很多 ensemble 等等的东西，在不同的状况下，等一下之后就会介绍。那总之这两句是长一样的哈，纯粹只是重复了。好，那接下来我们就发现，他就说这个重点就在于统计热力学是一个颗粒的理论。那为什么我们要讲动力学？颗粒的动力学在第10章，就是因为它都是这个统计热力学都是颗粒的理论，这样我们才可以去用颗粒的方式去运动方式或选择的几率去算。去解释，好，去解释这个平衡的状态，好，大概是这样。All right, so let's talk about quantum mechanics. But wait a minute, this is thermodynamics, not quantum mechanics. I thought we are going to learn. We took the course thermodynamics rather than quantum mechanics. Yes, but quantum mechanics provide the principle for molecular process. Okay, molecular is too small, so we cannot use our traditional mechanics to interpret this, to explain that. So we need quantum mechanics. All right, so this is a basis for the thermodynamics, statistical thermodynamics. All right, so actually I'm not expert in quantum mechanics. All we will do is using the result of the quantum mechanics. Okay, so we are not going to prove that. We're not going to explain that. We're just saying, okay, quantum mechanics says particle molecular has some behavior, and then we use that result to do the next. So we're just saying that we are using the molecular behavior with the quantum mechanics. All right, and we're not going to. It's not required. Okay, for this course. Okay, so I'm not an expert as well. So if you are going to trying to know better, know deeper in quantum mechanics, please take that original course. All right. 好，我们要接下来就使用的是量子力学的东西，但是实际上我们不是在教量子力学，我们只是用它的工具，用它的结果啊。那我不会有给大家太多的解释，因为我也不是专家，我只用它的东西，用它的结论来帮助我们去做接下来的事情。好，所以如果你真的要去学，想要认识更多 知道为什么它有这些现象，那你可能要去学一下量子力学啊，真正的课程。OK， 好，那sorry， quantum mechanics. One thing is that the one really important thing is that actually energy is quantized. What is quantized? Quantized means separated, and with a step. All right. Quantized means that it's not continuous. It's with a gap. All right. So you can imagine that your coffee has only certain temperature, like 30 degree, 25 degree, 20 degree. All right. So this is not continuous 30 and 29.9, 29.89. No. Imagine that your coffee is that, by the way, ED is quite nice. 哎，大家有没有觉得哪边的咖啡，哪一排咖啡最好喝啊？什么之类的，可以就是推荐我一下。虽然我已经喝到胃食道逆流了，但是实在是太好喝了。人生到老了以后，舌头的变化就变成不怕苦，比较喜欢香，很怕甜，妈太甜了。但是也是蛮喜欢吃一般的甜食，但我的意思是说，就不会像小孩子这么爱吃甜食，反而觉得苦还蛮香的这样。那我自己觉得伊利的咖啡就觉得好好喝哦。去意大利大家有没有去过意大利啊？就是我去意大利的时候，随便路上的那个摊贩，真的是摊贩哦，就是摊贩，然后就在那边弄咖啡给你，超好喝，每一家都好喝。我就想说，怎么会那么厉害？然后，而且我也觉得意大利面也很神奇，它就是节瓜意大利面，就乱炒一炒，然后蒜弄一弄，就超好吃的，好奇怪哦。然后后来我听说了为什么他们会那么好喝，是因为那么好喝那么好吃，那是因为当地的气候就适合那边的东西，节瓜我不知道是咖啡豆是吗？我不知道，总之就是很适合那边，然后就会有他们的或者橄榄油之类吧，我不知道，然后觉得好好吃哦。那所以而且真的是随便哦。那路边的一间小咖啡店，然后小意大利面店就超好吃而且又很便宜。然后每次看到路上走，就是一堆人都走在路上嘛，然后他们就站着，然后拿一杯小咖啡就 shot，然后就走掉了。然后真的是一个很神奇的一个国家。对，所以还蛮有趣的。那总之，我觉得伊犁目前是我觉得蛮好喝的一个咖啡这样。那如果有推荐我也可以，就是我也可以，应该说我不是专家啊，我不是专家，但是我只是觉得，总之觉得意的咖啡很好喝。那大家如果觉得有好的牌子啊，可以容易买得到的那可以推荐我一下，我可以下次试试看这样。Okay, so energy is quantized, so coffee only have certain temperature, right? This is weird, right? This is not true. But actually it is, all right? If you consider a microscopic level, all right? So why we think our coffee getting cold is continuous? Because the energy gap is so small compared to our habit, our scale, right? So you can see that it's actually quite continuous. But in the microscopic molecular getting cold, it's actually jumping from steps. All right. So small things like atoms, like molecules, have larger relative energy spacing, so they are quantized. Their energy are quantized. Yeah， 好，总之这中文的就是表示说，想象一下我们的能量是温度是阶梯式的变化，不是连续性的变化。那实际上连续性的变化纯粹只是因为我们看起来像连续，实际上是因为我们的尺度太大了，energy gap 能量阶其实的 差距实在太小了，所以让我们误以为它是就是连续的。但实际上，如果你是以分子的角度来看，或原子的角度来看的话，它们的能量的阶是有区隔的啊，它不是连续的，它是跳跳跳这样子的。那所以这个东西跳跳跳这种差距叫做 quantize 可能叫做量化吗？可能叫做就是有差距的。我不知道怎么样解释这个字，但是我曾经在一个音乐的软体上看过这个字，我觉得蛮有趣的，就是音乐软体，以前有的时候就是娱乐，然后就录一些东西嘛，哈，录一些键盘的东西，就可能就弹哆瑞咪，对不对？哈，但是人在弹的时候，哆瑞咪一定是，虽然我们以为我们很准，我们以为我们的拍子很准，但是它的拍子就是哆瑞咪，我们可能就是偏一点点或歪一点点，对不对？哈，那音乐软体就有一个功能叫做 quantize。它就会把你歪掉的变正回，就是100%完美的一拍两拍或是半拍这样，所以它就会校正你的东西，所以这叫做 quantize。我那时候就看到原来这叫做 quantize 啊，就是把歪一点点的东西给贬正。那所以这 quantum 有点类似这种道理。I don't know how to explain that in English. Basically, 好难哦。Anyway, so quantize spacing, okay, with the spacing. All right, so let's continue. So if we're going to talk about micro to connect macro from small scale to big scale, we need to consider macro state and micro state. Macro means big, right? Micro is small. Okay, so macro state we also call configuration. What is configuration? My configuration looks like this. Okay, configuration is something you look, okay, of a system. Something can observe is specified by the number of the particle in each the energy level of the system. All right, so the configuration or the macro state is determined by the particle in this system occupying different energy level. Okay, so before we talk about this, we need to see the system containing many particles. In total, n, all right, total number, n particle, and each particle belong to or occupy different energy level. So, for example, this is J level. J level has nj particle, okay? And you have J equal to 1, energy level 1, 2, 3, 4, 5, until n. So if you summon up all the particle within all the energy level, you have total particle number n. Okay, so this is quite, rule for this. All right, so number of identical indices, also known as assembly. Assembly. Well, it's just a name. Assembly means that assemble together, right? Assemble, gathering, make it one. Okay, so this is we also call this assemble. Right. So microstate is specified number of particles in each quantum state. Well, the quantum state means this. Let's take a look. So you have the macro state that you see, right? You see that in the real world, okay? And then actually a given macro state can be achieved by many micro states. What does that mean? Actually, your particle may in this system may occupy different quantum state. Quantum state means the small states that you can the particle can rest, can occupy. For example, you have certain energy level, maybe energy level 1, 2, 3, 4. Okay, and each energy level may have two different quantum states to achieve it, which called degeneracy. Okay, so degeneracy here, this energy level has two possible ways to achieve that, to have this energy level. Two possible ways. You either this particle can occupy here or occupy here, all the same. Well, represent the same energy level. It will give the same energy level. So it's called degeneracy 2. So you can say, for example, if this is energy level 1, 2, 3, 4, so you can say G1 equal to 2. All right. And then for the energy level 2, you have, in this case, 3 degeneracy that can achieve the same energy level. Okay, and here's 4, here's 5. Well, the number here are not necessarily always that. You can have 1 or 3 or 5 or 6 or 7. Well, this depending on the system that you have. And your particle can achieve, that can randomly choose each energy level. I mean quantum state. Each particle here has different quantum states. Okay. So of course you can see quantum states in the same energy level have the same energy. So if I will redo this slides again, I will put here and here, and here and here and here, and here and here. Okay, I will make it flat because they have the same energy. But now you see it's kind of it makes this up and down. So maybe not that representative, but both of them has the same energy level. All right, has the same energy. So you can see that by occupying different level, you will show different macro state to the real world. Okay, so you can imagine that different occupation can result in different given macro state. So so there's a nature question for this. How many possible micro states for macros for the given macro state? How many micro states for a given macro state? For example, if you have a macro state very rare, very not common, which means that the micro state may be really difficult to achieve, maybe very small amount of micro state available. So which means that it's in the nowadays, in the real world, you never see that happen because the probability, because the number of microstate is so tiny. All right, that's the thing. 好，我们要讲的就是巨观的状态跟微观的状态。要讲巨观状态跟微观状态之前呢，微观状态其实就是一大堆颗粒总合在一起，所以你可以想象那些颗粒占据不同的能阶，它就有不同的能量。那首先第一件事情要先看总 total 的值，就全部的 particle 的数量。怎么去算它的数量呢？就是每一个能阶的颗数，例如说第一能阶叫做 N1 的数量就是 N1 啊，第二阶的占据第二阶能阶的颗数叫做 N2， 反正把 N1 加到 NN， 有 N 个阶的话 ，N1 加到 NN 大 N 然后大 N 颗数加到第 N 小 n 的 energy level 就会是全部的大 N 这样子。好，然后把它加总起来。那这时候我们就会看来怎么样连接呢？我们现实生活中巨观的现象看到叫做 macro state， 我们现实中巨观的现象看到了，但实际上这看到的意思就是说，是由里面的颗粒去占据不同的 energy level。那这时候 energy level，如果今天大家都占据到高能阶的 energy level，所以我们就看到高能阶的状态，巨观的现象。但这时候又可以细分哦，同样能阶里面可能有，例如说5种达成的方式，都叫做第4能阶。那这个5种啊、4种啊的方式就叫做 degeneracy。反正 particle 选在这里面，它就是得到这个能阶。它有4种不同的方式，有3种不同的方式，有2种不同的方式，能达到这样的能阶。那对于 particle 来说，反正就随便选一个嘛，哈。好，那这时候我们就很想要知道，就是说，如果你今天看到一个巨观的现象，它有几种排列的方式？其实这很简单，就是如果今天排列方式越多种，表示说它几率达成的几率就越高。如果今天排的几率很小，哦，需要像中头彩一样才会排成这样子，那你当然就不会在现实生活中常常看到它。All right, so I will see you after 20 minutes. Thank you. OK，welcome back。最近天气变得比较凉了，终于比较不会不会流汗了。天气不错哦。好，嗯，最近比较凉，然后不会流汗，然后觉得脑袋会比较清楚一点。然后我有我常常在想这件事情，也不是常常啊，就是之前有想过一件事情，就是我去英国的时候，然后我就觉得说，为什么欧美国家的科技会比较发达？为什么他们的工程比较厉害？然后为什么？其实我觉得亚洲人、台湾人，大部分人都平均来说是更聪明的，比欧美我看到的平均来说，台湾人真的是蛮聪明的。可是为什么台湾的科技却没有欧美发达呢？这样，我那时候去英国念书的时候，就会有觉得为什么会这样？而且欧美又那么 chill，那我们那么奴，为什么我们科技为什么没有那么发达呢？然后我后来就就一直在考虑这件事情，然后我就在想说，哎，搞不好我们这边有很多天灾啊，就例如台风啊、地震啊，然后政治啊，所以我们就会一直在动荡不安的状态，就没有就是稳定的时间跟心力去发展这些事情。那我在英国看，然后英国跟美国就觉得哦，他们的天气好好，又不会太热，然后很 chill，然后就可以好好的想事情啊，做事情。我觉得这可能是一个关键，这样。那另外一个我也发现，我发现中文是一个非常不好用的工具。我发现中文超级不好用，因为它有太多的同音字了，而且我们的字都是我们的一个句子是连在一起的，所以你必须要自己去切割它。请问今天天气好吗？你要去分割，请问今天天气好，好吗？这样，那所以你必须要自己去切割，但是英文好像不需要吧？英文它自己都分割好，I am today is，就是它就是分割好，所以这是很清楚的。然后另外一件事情是，中文有太多的同音字了，然后很多的字句其实都是简写的东西。那所以我就觉得说，呃，很难沟通。其实说实在，这个在工程上的沟通上、合作上就非常的难，所以我们必须要去猜别人在讲什么，所以就花很多心力在这里，所以我就没办法花真正的心力在，例如说更有创意的研究发展，这是我自己的猜测，好，自己的猜测。那为什么呢？为什么会有这样的体认呢？因为我后来就是例如说我的小朋友他在问我一些中文的东西的时候，我发现我所有的解释都纯粹只是延长这句话的这个词的句子而已。例如说，他有一次问我真的是第一次吓到，就是他就说，请问时阶是什么？然后我就想说，什么是时阶？什么是石阶？大家应该听不懂吧？石阶是什么？是10个阶梯呢，还是石头的阶梯呢？还是什么什么？就是很奇怪。那我就开始所以他就一直因为从小朋友在问东西的时候，他当然不会给你上下文，所以他在问这个问题的时候，你就会发现中文是真的没有办法好好的沟通如果他今天是 stone stair，what is stone stair？那好像是石头的阶，OK，这个很清楚。但是我们却要说石阶，什么石阶？是然后10个阶梯吗？所以就是完全无法好好的沟通。然后，而且你看哦， 如果今天已经确定是石头的阶梯了，他就说什么是石阶啊？我说哦，那就是石头的阶梯呀。你看你这石阶这两个字，不就是石头的阶梯的延伸吗？应该说简写。那什么叫简写？简单的缩写。那缩写是什么？缩短的写法。所以你看，所有的词都是简写，再简写，再简写，再简写。所以实际上，我们的中文实在是非常的非常的没有效率耶。所以我那时候就是很就觉得说哇，就是那时候就觉得很不开心，就觉得说怎么中文害了大家一辈子这样。害了整个国家，害了那个，我那甚至有那应该说30几岁的时候是一个生气的年轻人哈，好生气的中年，好生气的中年人。那现在就不会了，现在就归于平静。那总之我就觉得说，哦，中文的那个混淆度实在是太高了，那我就觉得这是一个非常不利于沟通跟合作的一个语言，那就非常 diss 我们自己的文化这样。然后我要讲什么？对啊，diss 我自己的文化哦。然后我常常听到别人就说中文之美，中文之美。所以其实我觉得这些中文之美，其实建立在这种含糊不清的状况下。例如说，以前不是说什么标点符号的问题，例如说呃什么下雨天留客天，天留我不留，对不对哈？然后你用逗点就可以分割好。所以你可以看到，就是刚刚你同样一句话，你不同的切法，你会有不同的解释。所以实际上这表示说这个沟通的工具实在是非常的没有效率，所以我非常的非常的生气。大家听过这个故事吧？哦，下雨天留客天这个标点符号的那个，然后他们说哇，这个中文真是美妙啊！没有吧？是很糟吧？是很没有逻辑跟那个沟通的效率的吧？所以说，我觉得这些东西，这东西就造成了我们的科技就是没办法进步的比较快速，因为我们需要花太多的脑力去猜测别人这句话到底在讲什么，然后去分割他在讲什么，然后太多的简写了，太多的同音字了，所以这是让我觉得就是蛮可惜的一件事情。好对，讲完了，好。不大不大，那当然了，这都是以上都是我个人的乱想的猜测哦。那并不是真的就是这样，搞不好我们的科技没有别人强，是因为其他的事情，但因为我就找不出为什么啊，明明就大家都比较聪明，又或者是说，因为我们常常被训练要没事去猜测别人讲什么，然后去切割什么，所以我们才变得聪明。才会觉得哦，这个比较灵活这样。但一方面这样子受到这样的训练变比较聪明，但是却又整体的沟通却又是很难。好，Anyway，let's continue our lecture. Let's talk about thermodynamic probability. This is a really interesting name. Thermodynamic probability, W, is actually the number. The number. The number of microstates. All right. Leading to a given macro state. Okay. For example, the number of ways in which given configuration can be achieved. All right. So it's actually the number. Okay. So the number, the case number. Okay. So this could be 0 to infinity. Okay. This is unnormalized. So thermodynamic probability is not a probability. It's a number. All right. So weird. Yeah. So WK is the thermodynamic probability of the K macro state. So for example, you have many macro state. The second macro state, the third macro state. So if this is a third microstate, the thermodynamic, the number of microstate that lead to the macrostate 3 is W3. Okay? The true probability here, by contrast, is PK omega K. Sorry, WK over omega. Omega, which is the summation of K, all the K, so the total, and we didn't specify the upper limitation is that it's to the end, all right, everything. So now you can see that the true probability is a probability we are familiar with. So normalized probability. Probability 0 to 1. All right, so this could be 0 to 1, limited in 0 to 1. Okay. So 好，讲完了。好，所以说我们要讲的是热力学的几率。这热力学几率的名字超有趣的，它明明就是几率，它讲几率，但是它实际上是个数。也就是说，如果你今天有一个巨观的现象，你可能有很多巨观现象，可能第一种巨观现象，第二种巨观现象，第三种巨观现象，第三种巨观现象的达成这样子巨观现象的 microstate 有3种。那就是3 等于 W3等于3有4种啊，有4种，然后它 W3就等于4这样的意思。OK， 那这个答案就是这个数字可能是从0到无穷大数字啊，是数字，有几种方法。那所以千万不要把它以为是几率哦。那真正的几率叫做 P， 我们叫 PK。那 WK 除以 omega， 那 omega 就是全部的几率加总起来嘛，这应该蛮直观的。所以它是 normalized 的，它是被正规化的，它是被正规到0到1之间。好，这跟我们平常在懂的几率是一样的。你看我刚刚讲说 probability 就在边写边念，对不对？好，你看这种英文就很直观，就是你写出来，你大概就念得出来了。但是中文你如果不背，你写出来你也不知道，你不会看，你就不知道那个字怎么念。哦，所以这是又是另外一个难度。哦，所以我们从小到大，尤其是我小孩现在在写国小1年级，他就开始写那些字，他就必须要写注音符号，然后要写好多遍。我记得我小时候，我相信大家也是啊哈，每次写国字的时候都要写很多遍，很多遍。国写10遍。字写10遍，我就想说，如果不是因为那么难的字，又那么没效率，又那么难写，又那么难读，我们都学会了，我们都学会了。那你看，我就没看过，你看人家只要写 A 写10次，写26次就好，但是我们每个字都要写10次，国字，端中，要写那么多遍啊。那实在是太累了吧？我们花好多时间在这个上面啊，但又不得不做，因为这是我们的语言啊，所以这是这是我们自己的语言不太好。All right, so let's continue. So, in order to give you an example to understand the connection between macrostate and microstate, we use simple experiment called coin tossing. Flip the coins. All right, very typical. So imagine that we have 4 coins. We have 2 states. I mean, two choices, right? I mean, 2 results, head or tail. This is head. This is tail. All right? 正面或反面. Okay, so let's take a look. There's a total result table. A Okay, the macro state level. We have four. We have 4 coins. 4 coins, and we assume that the N1 is the number of head. N2 is number of tail. All right. So macro state means that you have 5 possible macro state. The result. Okay, the result. You can have either 4 head, 0 tail, 3 head, 1 tail, 2 head, 2 tail, 1 head, 3 tail, 0 head, 4 tail. So this is final results. K equal to 5. I mean, K equal to 1 to 5. Okay? And the micro state is that different coin. Coin 1, 2, 3. So it's H, 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 H. All right? So you can list all the possibility here. And 3 head, 1 tail. 3 head, 1 tail, 1 tail, 1 tail. All right? So you can list everything. So this is micro state. So you can see that how it is, how it works. You have different micro state, but achieve the same macro state. All right? So the thermodynamic probability is 1, 4, 6, 4, 1. You see 1, 2, 3, 4, 5, 6. 6. So you have thermodynamic probability for case macro state level 3 are 6. Okay, and true probability is, of course, sum and not together 1, 4, 6, 4, 1. You got 16. Okay, so you got 16 as an omega. And you divide by 16. So you got true probability in the end. All right, so you can see that how to get all this value, we can introduce several mathematic expression for this. So macro state has N1, N2. Their relationship is N2 equal to N minus N1. Again, N is the total number. Okay, and you have yellow for tail, right? And head. Okay, so how can we get thermodynamic probability? Number of way. Remember the permutation and permutation of probability you learned in senior high school. 4 factorial divided by 3 factorial, 1 factorial. Of course, this is 3 means number of head, and 1 is the number of tail. Of course, here is 4 factorial divided by 2 factorial become 6. Okay, and so now you can get every thermodynamics probability, and the omega is WK from K equal to 1 to in total 5 become 16. So that's how we get 16 and get the true probability in the last column. Okay. Oh, also, all heads and tail are indistinguishable in this case. So which means that this is not H1, H2, H3, or tail 4. No, they are all identical. Okay. Indistinguishable means that you cannot tell the difference. Okay, so they are all the same. So this is the same as that. Okay, no separation, no distinction. Yeah, anyway, I guess you understand this. 好，所以我们为了要让大家了解巨观现象跟巨观状态跟微观状态，我们使用的是用一个很简单的丢铜板的实验。假设有4个铜板，正或负，正面跟反面，正面叫做 head， 反面叫做 tail。OK， 然后呢，我们总共会有几个结果呢？有4个的话，有几个结果？ 就只有5种啊，要么就是4个头，4个正面，要么就是3个正面，要么就是2个正面，要么就是1个正面，要么是没有正面。OK， 那这样的状况下有几种可能性呢？就叫做 microstate， 就是微观的状态。有几种？第一种当然就只有1种状态啊，就是全部都是正面，那没有任何选择。但是如果你今天是3个正面1个反面的话，那你就有这4种状态。那你要怎么样得到这4种状态呢？我们就使用我们的排列组合跟几率在高中的时候教的嘛，哈，4阶除以3阶除以1阶，那这个3阶其实就是3个正面，1阶就是1个反面的意思。那这边也是一样。好，那得到这个就可以得到这个 WK 所有的值，那把全部加总起来就会是我们的 omega， 然后除以每一个 WK 的话，就是它的真正的几率。那应该蛮简单的哈。那注意一件事情，就是我们这样子看的意思，就是说我们表示说这个 H 啊哈，就是正面跟反面是分不出来的。那我们不会说这是第一个铜板的正面，这是第二个铜板正面，没有，我们就反正正面就是正面，大家的正面都是一样的，大家的反面都一样，所以我们是无法分辨的，它是没有差别的，就是给你的是同一个巨观的状态，这样子的意思。好，那这就是帮助大家了解巨观和微观之间的关系。Next, so let's dig further. Okay, we continue to describe the thermodynamic probability. So as you can see, NJ is the energy level or microstate level difference. But if you have bar, which means that the average occupation number, averagely, the average number of the head or tail, if the J equal to 1 for head, J equal to 2 for tail. So what is the average number you got in this experiment? Actually, we always say this is expected value. So during this coin tossing problem, the expected value for this problem is 2 head, 2 tail. I guess you know that, right? So this is expected value. Actually, it's really similar to our material, all about expected value. All right, but I will give you more detailed introduction for this, explanation for this. Now, the occupation number for the K state, K macro state, is that, so if you have one, J, if you have the occupation number for 1, N1 bar, N1 bar means J equal to 1 means that you have 1, how many expected value for head case. So this is a head case. Let's take a look. As we say this is 2. So how can we get this? All we can do is trying to determine the number of head, times its own true probability. So you can see 4 times true probability, 3 times true probability. All right, that's it. All right, so you can get 2. So you got 2 head for this coin tossing experiment. You expect 2 heads averagely. I guess you understand what I'm talking about because it's easy. You have been taught in senior high school. All right, so the W, how can we get W? CNN1. N1. Well, so I just give you some review because you have done that in the senior high school. The W is CN N1. I don't know how to pronounce it. Cn take N1, I don't know. Cn 取 N1, I don't know. Cn 取 N1. All right, so we also can write it down in this form. But the actual expression is, I have been written this n factorial divided by n1 factorial n minus n1 factorial. So this is n2. N factorial divided by n1 factorial, n2 factorial. All right, so we call this binomial coefficient, coefficient. All right, so we call it binomial coefficient. And so you can find the W mix, of course, when N1, N2 are the same, 2 factorial 6. So you can imagine that if you draw all this value, 1, 4, 6, 4, 1, okay? And you draw the figure, you find that the W to the head distribution like this. The highest is 2 head. Okay? I guess you understand this. No problem, right? And you notice that this is symmetric. Symmetric. Maxima is the most probable configuration. No problem. This is too simple for you. 好，我们要继续讲下去哈，就是我们现在想要找的是期望值。你丢了这4颗铜板，你预期会得到多少的正面呢？那就直接把每一次的正面乘上它的几率加总起来，那这样起来就会是2，2个 head， 这没有问题，大家都知道。我们大家复习一下，高中生教过的 Cn 取 N1 哈，那就是 n 阶除以 n1 阶乘上 n 减 n1 啊，然后就可以，其实就是 n 阶除以 n1 阶除以 n2 阶了哈。我们叫它 binomial coefficient， 这个不重要哈。然后呢，我们发现最大的值最大的 W 就是6，在这里。然后我们把这张图画出来，轴就是几颗啦哈，就例如说一颗正的，跟2颗正的，跟3颗正的，跟4颗正的。为什么这样？0颗正的，1颗正的，2颗正的，3颗正的，4颗正的 ，OK 的几率正好就是多少？14641啊，14641，然后把它画起来，就发现它是一个对称的分布，然后最高值就会是它最有机会出现的几率的状态，应该没有问题吧？哈，太简单了。Next, let's consider the most probable configuration. Previously, we talked about 2 coins, right? 2 coins. So our W for 2 coins is this 6, right? N equal to 4. Only 4 coins. We only have 4 coins. The distribution like this. How about 8? 8 looks like this. If you have 8 coins and you flip, and your chances looks like this. How about n become 1000? How about 1000? 1000 looks like this. Okay, so let's take a calculation, all right? So here, 4 factorial, 2 factorial, 2 factorial equal to 6. So you know that most probable is 6. How about 8? 8 factorial, 4 factorial, 4 factorial equal to 70. Okay, now, what is the W mix for n equal to 1000? Of course, 1000 factorial, 500 factorial, 500 factorial. Okay, suppose the W mix equal to this one. What is the value? It's difficult if you don't have the calculator, right? But yeah, you can calculate, and it will be really, really big number. But if the ancient scientific ancient mathematician didn't have the calculator, how do they determine the value? They determine that by using mathematic technique, ln log. Natural log W max, because it's all multiplication, right? So try to make multiplication become plus and minus. So natural log 1000 factorial minus 2, natural log 500 factorial equal to what? Okay, so this thing, another thing we need to do is that there's a Stirling's approximation. It's found in, we can find it in Appendix B. This Stirling approximation is so important mathematic technique we will use in frequently in the following sections. Okay, this is the mathematic tool that the mathematician found. Natural log n factorial is approximately equal to n natural log n minus n when n is big. When n is large or big, anyway, big is easier. Okay, when n is big, natural log n so this is called Stirling's approximation. So if we substitute this 1000 here, become 1000 natural log 1000 minus 1000. Okay, and this is 500. This is natural log 500 factorial approximately equal to 500 natural log n minus 500. Okay, what will it be? It will become 693.15. Okay, so natural log W max equal to 693.15. And what is the, so if we further change the base, this is natural log. If we change the base to log 10, it becomes log 10 exponential times natural log W max. And log 10 exponential is 0.4343. And this is equal to 693.15. And you time together become around 300. So what does that mean? Log 10 W max equal to 300. So which means that W max equal to 10 to 300 power. Wow, this is really big number. Really big number. So you can see that the distribution for n equal to 1000 is like this. And this value is 10 to 300 power. Wow, this is so big. So you can see that this 10 to 300 zone is actually totally random region. And if the other region is older the region, what does that mean, older the region? It must be here, must be tail. And here become head. All right? And this must become head, tail, head, tail, head. So you can see that this is random region. This is older region. Okay? You can see that this definitely much easier to occur in our real world because this entropy is higher, right? This is too older, so it's never happened. Okay, so you can have a conclusion that n1 equal to n2 is the one that almost always occur. Almost always. Almost always occurs. Compared to, you see, you have 10 to 300 times. I mean, 10 to 300 cases that can achieve, but very rare number can achieve the order the region. And this is only 1,000. Imagine that we have 10 to 25 number of particles in a 1 kilogram, a kilo more. So you can see that, you can imagine this is so high in the real world. So this region, random region, is almost always occurred in the real world. 好，我们现在讲就是最大几率出现的东西的状态。我们刚刚讲到四颗硬币，就是有6种机会，6种 case 会出现，8个的话会有70种。那我们来看看这个 n 如果是1000的话会怎么样 ？W max 会长这样子。那这个东西我们用计算机算会很容易，但是呢，如果今天是古代的科学家就没有计算机，他怎么算呢？他们取 log 然后变成加减，然后呢，他们就使用一个叫做 Stirling approximation， 就是一个数学家他做出来的东西，他觉得我们就可以使用它，让 natural log 的 n factorial n 阶会约等于 n 乘上 natural log n 减 n， 然后它这个会越来越准，如果 n 是很大的一个数字的话。好，他们就用了这个，结果发现 natural log W max 会等于 693.15。那我们就来试试看，这到底是如果把这个底 natural log 的底换成 natural log 10的话，会怎么样呢？答案是300。好，那300的意思就是说 W max 等于10的300次方，超大哦，超级大。那其他就是基本上很小。我们说这个10的300次方总可能。10的300次方总可能可以达到最大的、最有几率达到的状态。那大家可以想象一下，这是正负嘛，哈，所以这 n1 是正面的数字，所以你可以看到这边的话，基本上就是几乎没有头，所以就是反。那如果是这边的话，就是正，所以这边很规则，对不对哈？这些小几率的地方是很规则的，但如果是大几率的地方，它就是有的时候是正，有的时候是负，有的时候正，有的时候是反，所以它是大几率的随机的区域。那这边可以看得出来，随机的区域基本上是永远都会出现的，因为它的几率实在太高了，跟其他的相比，尤其是在这才1000哦。我们的现实生活中的颗粒数是10的25次方等级的，那不就是更爆炸多吗？所以说基本上是不可能会出现 order 的状态，一定要是人为去改变它。好，那如果今天是一般的状态下，都是随机的比较多几率。Alright, so let's repeat that again. That this is the total region, random region, and this is the ordered region. So the ordered region almost never occur. So you can imagine that omega summation WK approximately W max, especially when the n is so big. Okay? Because the cases here are too small compared to random region. So you can almost say, omega, the total value is almost equal to W max. So you will never see something else happen in the real world. W equal to W max when dW n1 divided by dn1 equal to 0. So which means that we want to find this value, peak value. Do the differentiation. We can do that. Okay, and it's big. Now if the molecule in the gas, the particles are normally identical and indistinguishable. All right, so in the gas, particle always like coins. Okay, they're coins. You cannot specify which particle is which. And then, so you can imagine that the molecular, the molecules here has so many types, so many states. Okay, so you can have one N1, N2, N3, N2 to Nn. So you can say that the W is actually can be written in n factorial total, right? Divided by summation. Sorry, not summation. Multiple times. Okay, multiplication. Mj factorial, right? Okay. Here, sorry, missing one factorial here. So you can rewritten like this, and this summation is actually summing up together, but the pi here is multiple time together. All right. So this is a symbol. We explain this in symbol. All right. Small notes here. Here is a molecular in crystalline. Solid normal can be distinguishable by location. Okay. In the gas, the molecule flying around, okay, in the container, so you cannot identify them. So you cannot distinguishable for them. Distinguishable. You cannot distinguish the gas atoms, but solid has structure. So you can see the structure looks like this, and you can identify that because they can have the neighbors. When you have a neighbor, which means that you know its location. So solid can be distinguishable. So you can see that indistinguishable and distinguishable may have different way to do the statistic, to do the analysis. All right, so this is different. So which also tell us we cannot use the same statistical way to do the solid. All right. 好，我们继续讲最高几率的状态哈。那我们刚刚说这个，如果 n 超大的话，比1000还要大，那不就是这边的几率实在是超级大吗？或是能达成这样的状态的 case 的数量超级多。那跟这些均匀的状态比起来，实在是差太多了。所以我们甚至可以说，总几率其实基本上就等于最大的几率了啦，因为其他的都相比来讲就是超级小了。那所以我们可以这样写，那 W 等于 W max 的时候，其实就是这个函式的平均，不讲错了，微分等于0的地方，然后叫它等于0，它就是极值嘛哈，大家可以这样可以知道。然后接下来呢，如果我们把硬币的实验映射到、投影到，或是应用到气体的状态下的话，气体的分子在容器里面飞来飞去，我们也不能知道它，我们也无法分辨这颗跟那颗有什么差别嘛，对不对？因为它飞来飞去，一直在混合中。那所以说可以跟硬币的实验很类似。假设它有这么多种状态，不是只有正反的，它有这么多种状态，它的 W 就会写成这样子。那这样写的话比较难看，也不会比较难看啦。总之就是它会把它写成一个式子，就 n 阶除以派的 n 阶 factorial nj 阶啊。那这什么意思呢？那派就是全部乘起来，这边都是乘的嘛，哈，乘。那 sigma 是加，好，所以这个派，请大家就是熟悉它一下。那另外一个值得注意一点就是 molecular 如果在晶体的状态下的话，是可以被分辨的哦。为什么？因为我们常说啊，它有特定的结构，对不对？哈，晶体结构，所以你可以知道它们的结构，它们的邻居在哪里。既然你知道它的邻居是谁，邻居在哪里，表示说你可以分辨。所以说它们 固体跟那个叫什么气体，他们会用不同的统计法，因为一个是可分辨，一个是可分辨，一个是不可分辨，所以你的统计法当然会不一样，你的几率当然会不一样。好 ，Next let's talk about assembly of indistinguishable particles. Okay. The system containing fixed number n of distinguishable particles. So now we're not going to say about the coin, but now we're talking about actually the kind of material system. A material system has fixed number of n, no problem, and fixed volume v, and the macro state in the system is defined by. So if we say that the system has certain internal energy, we fix the internal energy. So actually, this system is defined by N, V, U. Okay, so N is particle, you fix that. Volume is fixed. Energy also fixed is there. All right. So we want to see how many possibility to achieve this state of NVU. Okay, we want to see how many ways to achieve this state, NVU state. Okay, so N of course need to be conserved all the time. Volume, energy also need to conserve all the time at this case. So Nj equal to N, Nj summation equal to N, no problem, right? I have specified this in the previous few pages. And then here is conservation of energy. Of course, different energy level has occupied different atoms, right? So Nj is the energy number of particle occupy energy level J, and of course epsilon J is the energy level, energy of the energy level. All right. So if it times together, which means that all summation together become the total energy. I think it's okay, right? Conservation of energy. So now, if we can have an example, if you have the really small, tiny container containing only 3 particles, A, B, C. Okay, but actually they are not distinguishable. So they are flying around. They can occupy different energy level. Okay, and also you know that this, when you measure, okay, you measure this system has U equal to 3 epsilon. 3 epsilon. The epsilon is the unit, all right, for certain energy unit. 1 unit energy, 1 unit of energy. And you see that the macro state specification is that for the energy level 0, ground state, if, we just say if, so this is a model, toy model we play, okay, ground state. If the ground state, energy level 0, has 0 energy, if this material has this kind of properties, okay, energy level 0, energy level 0 has 0 energy, energy level 1 has energy epsilon, energy level 2 has energy 2 epsilon, energy level 3 has energy 3 epsilon. Okay, so each energy level has more and more energy. Okay, so if you follow this setup, what kind of possibility that if you see this material has U equal to 3 epsilon? So let's take a look. If there are the first one is 2 particles occupy the ground state, no energy at all. and one particle occupies 3 epsilon. So summing up together, total U equal to 3 epsilon. Yes, it's okay. And for second, for 0, 1, 2, yes, 3 epsilon as well. Or 3 of them combine, occupy energy level 1. You also get 3 epsilon. So this is macro state, the possible macro state. All right, but each of them has different micro state. You can see that to achieve this 2, 1, 2 and 1 can be what's that? A, B, C. Oh, so either A, B occupy 0 energy and C occupy 3 epsilon, or B occupy or A occupy. So there are 3 possibilities to achieve this macro state, and etc. etc. All right, so 3, 6, 1, and true probability is 0.3, 0.6, 0.1 because the omega equal to 10. 3 plus 6 probably 1. All right, so you can write down this table by yourself. Okay, I will see you after 10 minutes and I will continue this lecture. I will translate this lecture, this page in Chinese. Thank you. When
我看不懂那个字是什么。
其实我就写错了，好，感谢你加，这是可以，这可以加分的，因为我写错字了，不知道怎么少写一个 n，请告诉我你的号码。314
613
613
041。
041，谢谢。 Oh, okay. One thing I want to say, I forgot to say, is that next week will be the midterm, right? Midterm 1. And from next week on, we will have a lot of events going on. For example, master student administration interview. So next week is midterm 1. Next week, I cannot give the lecture. All right. So I will give you the video course. All right. I'll give you a link, and then you can see the content of the link. All right. 好，就是说从下礼拜开始，我们学校有非常多个活动 ，OK， 那个活动包括硕士班的口试，硕士班的面试，然后各位就是这样进来的嘛，硕士班面试那时候也是礼拜3，大家还记得吗？然后还有什么运动会停课啊，什么之类的，反正好多一大堆有的没的，这样，所以。但是因为又减少成16周，所以我必须要给大家，那我不能上课的话，我只能给大家去年或者前年的线上的课程，那请大家回家自己看啊。那不过如果你有发现我之前有放那个2024的固热器，你会发现它当时的我跟现在我讲几乎都是一样，因为毕竟已经教了12年了哈，所以东西已经开始就是怎么讲？那什么 converge 叫做收敛成一个，我也不敢说最佳状态啊，但是每次讲话每次讲大家都差不多这样，而且里面的故事都差不多一样，每次讲的笑话都差不多一样这样。那对，就这样。所以说下礼拜是考期中考，下礼拜就是不用上课，但是请大家到我会给大家 link 然后请大家看上面的我去年或前年的上课内容。好，那请还是要看不然的话我接下来上课你就会听不懂哦。那下一次的见面将会是下一次要上课的见面将会是11月12号。All right, so I will say I will see you. I will see you on 12th of November. All right. The course will restart. Personal, I mean, face-to-face course will be on 12th November. All right. So next week, 29th of October will be midterm 1. 5th of November will be video course. All right, video course. The next week, 12th November will be our next lecture. And 19th of November will be the sports event, okay, in our university. So video game. And 26th of November will be midterm 2, okay. So所以啊，下个月开始我们只能上1次课，然后要有2次 video 的那个课程，然后26号1个月后就期中考，第二次期中考。And then I will see you on 3rd of December again. And then I'll go into conference, video again, and then final. Oh my God. So actually I will see you. Let me take a look. I will see you 1, 2. Oh, so before this semester end, I will see you only 6 hours. Oh, interesting. 好，因为很多事情哈，那总之就是这什么硕士班口试，然后运动会停课，然后不好意思，我要去研讨会，所以3次没有办法上，所以就是要有 video 的。那这样看下来，去除掉期中考1、期中考2跟 final exam 这3个考试以外，我只剩下2次的面对面的上课，也就是说这一堂课上完以后，我只剩跟各位的相处时间大概就是6小时啊，6小时，时间过得好快啊，对，就这样。好，那我们就继续下去了哈。Okay, so let's continue our lecture. All right, so now this is how we managing what kind of how many ways, how many micro states that can achieve certain macro state label. Okay, macro state things. So as you can see, if you specify N, specify V, specify U, you mean fix that 3 value, you can find the most probable way to achieve the state you given. All right? 我刚刚是不是没有解释中文？好，那就是说，假设有一个系统，这个系统我们要指派，就例如说固定它的里面有几颗，就是质量里面有几颗 particle， 几颗颗粒，体积也指派给它了。然后这时候我们去量它的energy U 得到了，好，我们再不动它，它就是这样 fix 住了 ，OK 就是这样。然后我们这时候就看，在这样的状况下里面呢，NJ 等于 N J 就是 energy level， 就是能阶，有不同的能阶 ，NJ 就是占据能阶的颗数，那总共加起来当然就是 N 咯，这没有问题，我们叫它质量守恒particle 的守恒。那接下来呢 ，NJ epsilon J 什么意思呢 ？NJ 还是一样，就是占据能阶的颗数 ，epsilon J 就是能阶的能量。那把它相乘起来，就是那个能阶所有颗粒的能量。那当然加总所有的能阶就会是全部的能量。那我们叫它能量守恒。OK， 好，那假设有一个很小的玩具模型，它只有3颗 ABC 3颗，然后它的能量是3个单位能量，叫做 epsilon。好，那这个 epsilon 呢，这只是一个能量单位就是一个单位而已。那假设这个材料的状态是在零阶，第0阶的时候是没有任何能量的。接下来就是第0阶，第1阶的话，它就是1单位能量，第2阶就是2单位能量，第3阶就是3单位能量。那总共是3单位能量 所以说就只有几个 case 是要么 A occupy 第三个，要么 A 占据第三阶，要么 B 占据，要么 C 占据啊，就有3种状况。那还或者是有其他种啊哈，对，你就可以就是把它排列下来，排列下来以后算出它的个数以后加总起来就会变成 omega 再除以它的个数，除以它的各自的个数就可以得到它的最的几率真正的几率。好，那终于我们就可以就是这样，等于是说你只要指派 NVU， 你就可以得到就是最disorder 就是最 random 的状态最随机的状态，那是它最有可能出现的状态，因为它最多机会Okay, next, and then we call the average method called ensemble. In Chinese, 系中 Well, it's kind of a concept, but the concept sounds difficult, sounds complicated, but it actually is simple. Just average. Ensemble average. Okay, what is ensemble? Let's take a look. So when you do the actual experiment, so if you want to make really accurate measurement, you should actually measure for long time and average the result that you measured. Okay, for example, if you have a really small container and you have 3 particles inside it, and we want to measure pressure. Okay, so actually, when you measure pressure, actually you will the pressure actually come from the particle hit the wall, right? Hit the wall. So if the time you measure the particle did not hit the wall, you will have less pressure, right? So actually, the value you measure of the pressure in different time may vary. Okay, so for long time average is actually the value you trust, right? Your result will be long time average value, right? So this is the way the experiment or the real world that we are going to do, okay? But in the theoretical, numerical world concept that you cannot, you don't need to measure so many times. How about that? Because this numerical world, theoretical world is kind of in your head, right? So you can imagine that you have many duplicate copy. You have many clone of the system. For example, you have many the same system, and you do the screenshot once, then screenshot, and then you measure the pressure 1, pressure 2, pressure 3. So each of them also has different value, right? And your ensemble average value will be approximately equal to your P long time average pressure. So that's just the concept. Okay, just the concept. 好，现在要讲的是 ensemble 系中。系中这个名字听起来是什么很复杂哈？其实没有很复杂，它其实就是平均而已。它只是一个告诉别人说，我们这样做是对的啦，我们这样做是合理的，这种感觉而已。好，现实生活在量测压力的时候，假设你在量一个很特殊的系统，它是只有3个 particle， 你要去量它的压力， 但是有的时候，假设你量的很好，一直量，但是你在量的时候，如果这个 particle 正好都没有碰到那个墙，那你压力为零呢。好，但是有的时候只碰1颗或碰3颗，你压力其实会是起伏的。所以什么叫做这一个系统的压力呢？我们的结果就会是我们要量超久 ，long time， 量超久，然后去平均它，那就是 OK， 这个系统的压力是多少，对不对？好，这是我们的做法。但是现实生活中做法是这样，但是系中，也就是说我们在做 statistical thermodynamics 统计力学，它其实是一种概念，我们不需要去量那么久啊，我们可以想象就是说，我们假设有这么多个 particle，这么多个系统。都是同样的系统，我们有很多个复制系统，这个复制系统一字排开，然后我们只要量当下每一个复制的系统的压力，把它画出来啊，那这不是也，你不觉得这两张图非常像吗？那虽然它不是有时间序列的，但是它的代表性其实非常类似的。那一样，我们把这些值都做平均，我们就可以得到约等于 long time average 这样的值。好，那这基本上就是说，因为我们统计热力学就是假设就是我们有非常多种可能，那非常多种可能，我们只是去平均它，就是计算它的期望值。这个期望值其实基本上就是你 long time average 的答案。其实系中这种东西就是很简单，我们的概念都很简单，但是讲的很复杂。其实纯粹只是大家就是说，我们系中算出来的答案，跟你平常量出来的很久的答案其实是会一样的。好，就是这个观念而已，就只是这样而已。OK， 不用太紧张。So let's talk about type of ensemble. The type of ensemble is actually defined by the parameters that you fix. Okay, so microcanonical ensemble fix NVU. Actually, we talked about this before, right? In the previous 2 pages. Okay, so an isolated system surrounded by rigid thermally insulated wall. So you can see that in this case, the particle will be the same, volume is the same, internal energy will also be the same because there's no energy exchange across the wall, right? We also call this NVE energy rather than U. Sometimes if you determine perform the molecular dynamic simulation, sometimes you will choose NVE. Okay, it's actually called, and it is actually microcanonical ensemble NVU. Well, they're all the same. And another thing is that canonical ensemble constant NVT. So if you fix N, fix V, and fix the temperature, and the energy may change due to other things, other change of the condition. So it's a closed isothermal system. And of course, in the real world, we tend to use this NVT because it's easier for us to control N and V and T. Right, so it's called canonical ensemble, but grand canonical ensemble means that you will fix your nu, okay? Which means that you fix your nu, but which means that you can have the exchange of the mass. So the N may not the same. So open isothermal system. But again, this is really difficult. So typically we will choose this to, take a closer look. I mean, we will talk about this here. Sorry. Wait a moment. Okay, we will talk this two. All right, microcanonical ensemble and canonical ensemble, and then we are not going to talk about this because this is a little bit too complicated. So we are not going to talk about that. All right. So firstly, for the isolated system, so the first one, microcanonical ensemble. there is some assumption for microcanonical ensemble because MVU, right? All the accessible microstate, quantum state are equally probable. No preference. Okay, we assume that. So which means that you see here, all the energy level here, they are all fair. Okay, so accessible means quantum mechanical allowed. Okay, accessible means you can occupy this level, this level, this level, this level. But there's no accessible for the 4 level, energy level 4. This is not accessible. The 4 energy level 4 is not accessible. All right. So just saying that accessible energy level has equal probability. And we also assume that long time average of all the property will be equal to ensemble average. OK， 好，我们这边要继续介绍有不同种的系宗哈，有 microcanonical， 我不知道怎么翻译啦哈，我真的不知道怎么翻译，对不起，为正则，反正正则这种东西我也不知道它的意义是什么哈。总之它就是 microcanonical ensemble。那一个是指定 NVU， 当然就是对应到独立的就是不会独立的系统，然后它是不会变形的墙，然后它也不会有任何的温度跟热的交换，所以 NVU 是固定的。那正则系中呢，它就是固定 N 跟 V 跟温度啊，这个跟我们人类的做实验比较类似。那它是一个关闭式的等温的系统。那 Grand Canonical 的话就是比较难，它是 open 的，所以它是 N 会变化，然后它是 constant nu， 它的那个 chemical potential 是不会变的啊。那这比较难，所以我们就不考虑了。我们今天不讲它，那我们只讲这2个，为正则跟正则。然后呢，我们来介绍一下，就是为正则的话会有一些假设，就例如说，我们假设它的每一个可以被占据的能量，它能阶都是一样的几率，没有偏心。那这边的 accessible 的意思就是说，题目规范的，就是只要题目规范之内的，它可以达到的，叫做 accessible。那我们也就是说，只要考虑这一部分就好，你不用考虑就是绝对达不到那些能阶。那只要是能达到的能阶，它的几率都会是一样的。达不到，那当然几率就是0，这样的意思。好，然后我们还假设刚刚讲过的哈，就是我们的系中做的平均会等于我们现实生活中量很多次的平均。好，这是我们刚刚解释的。Alright, so let's continue describing to summarize the microcanonical ensemble. Alright, so we fix NVU and the probability Pi for any given state is Pi equal to 1 over omega. Of course, the Pi is probability. We mentioned that omega is the total cases, and 1, of course, is because there are only one, for that state. So all the quantum state are equal probable, equal possibility. Okay, so the ensemble average pressure is actually ensemble average pressure P bar equal to omega and sum them up all together. All right, so this is PLT average. All right, so that's basically what I mentioned in the previous stage. And then the energy E bar equal to 1 omega sigma I E I. Okay, the E, of course, is long time average measured energy. All right. So yeah, so that's it. Right. 好，总之就是说啊，哈 ，microeconomic ensemble 其实就是之前我们讲的那一页，然后很简单，就是每一个 state 都有，每一个那个 micro state 都有一样的几率，那所以基本上我们就算它就对了，我们就算它有几个几率，再乘上它的 pi， 它的对应的能量，对应的能量，对应的压力，反正一样也是期望值嘛，这就是期望值啊哈。那因为它都公平，没有任何的 preference， 没有任何的喜好，所以它能量就只要去算它的个数，然后直接乘上它的相对应的压力，相对应的能量，就会得到它的 ensemble average 了。你知道它的 ensemble average 其实就是我们的一直想要求的全部的，就是实验的 long time average， 实验的量很久的平均的压力或量很久的平均的能量。OK， 所以基本上 microcanonical ensemble 是还蛮直观的。接下来讲的就是 canonical ensemble 比较难，比较需要讲解，那我们就开始咯。哈，这是另外一个 ensemble 了。So next we are going to talk about the second ensemble, which is a little bit more complicated. So I will spend some time to discuss this. All right. The canonical ensemble, I'll give you an example. If you have a two-particle system, the two-particle has position momentum coordinates. Well, you can imagine that this is a different direction. So you can have momentum to X direction, Y direction, Z direction, okay, in the system. And energy is interchangeable with surrounding. Okay, so which means that your energy can be exchanged. Or you can say this is thermal water tank. So which means that if your energy decreased, the water will give the energy to the system. So the energy will be always exchanging through the wall, and also means that it is MVT. MVT canonical ensemble. Okay, so this is the example from textbook. All right, I will give you two canonical ensemble in this lecture. All right, this is the first example from the textbook. Now, let's continue. Okay, if you have two particles and each of the particle may have three momentum to X, Y, or Z. So you can imagine that maybe this direction is momentum 1. This is momentum 2. All right. And each of them may have different choice, 1 or 2 or 3. All right. So the possibility, the quantum states may have such many. Okay. Either 1, 1, either 1, 2, or 2, 1, or 2, 2, 1, 3, 3, 1, 2, 3, 3, 2, 3, 3. Okay, so there are such many quantum states. And you can see that degeneracy for 1, 1, only 1, right? So this energy level, only 1 degeneracy. But for this energy level, you got 2 degeneracy because you have 2, 1, 2, or 2, 1 cases. 2, 2, 1 degeneracy. 1, 3, 2, 3 has 2 degeneracy for these 2 energy level. 3, 3, 1 degeneracy. Okay, so this is basically you list all the possibility. Okay, so you can see GI is 1, 2, 1, 2, 2, 1, 1, 2, 1, 2, 2, 1. Okay, then because there's no specifying the energy, right? So actually this material may have different energy. Okay, so how can we get the energy for this system at this and this condition, we're using ensemble average. We're using ensemble case. You see, we have A, B, C, D, E, F, G, blah, 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 to Y, such many. How many? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 25. We have 25 clone of this system. And then at the time T, oh, it has A, B, C, D, E, F, G, and A is 1, 1, B is 2, 3, M is 2, 2, W is 3, 2. All right, so this is time T. Okay, so basically, actually, you can just get the energy from clone A. You can get energy from clone B, EB. Okay, so all you need to do is determine all of them and average. And you do the average of them, you can get the approximately E bar. E bar is also can approximately equal to long time average. Okay, so sigma I Pi EI, again, expected value, right? So this is ensemble average energy, and it will be approximately equal to E long time average. Okay, and what is a Pi here? If you have larger ensemble clones group, you can have more accurate E bar. Okay, so now this is time T. Why I going to write down time T plan here? Actually, we don't need time T plan here. The reason why we put another time T plan for the ensemble group is that I'm going to show you why this work, why this is reasonable, why this is trustworthy. Because you can imagine that the same ensemble group in time T will has exactly the same distribution, probability distribution at time T plan. You can see that although A is different here, A at time T is 1, 1, at time T plan is 2, 2. But overall speaking, you can still find 1, 1, 1, 1 in C and K. So you see the distribution for the two, for the same as ensemble group at two different time actually are the same. So actually this is we don't need the T plot. We only need T time T. The reason why we put here is that we're going to show you actually from the averagely, from the macroscopic view, these two are all the same. Okay, so this is the concept of canonical, the concept of ensemble. OK， 好，我现在要讲中文哈，就是说我们现在来介绍 canonical ensemble 正则系中啊，只是给你一个例子，这是课本的例子。下一个是我从网络上找到另外一个例子，我觉得更好。不过这两个例子其实基本上差不多的。好，我们来看一下，假设这边有两个 particle， 然后这 particle 呢，它有3种状态，3种 moment 哦，就是动量的那种状态。你可以想象它就是 x 方向或 y 方向或 z 方向好了哈。然后呢，这就是这是选到1方向，这是选到2方向，大概是这样子。好，那这时候我们就来看呢，如果你今天有3种选择，你有2颗，你 either 就或是1、2或2、1或2、2这样排下来。当然，每一种状态都会每一种组成都会有给你一种能量的状态。 那我们就说它 energy level。好，然后接下来呢就发现，哎，这样子的能量状态会有2种组合，哎，1、2或2、1，那也就是它的 degeneracy 就会变成2咯。所以你可以看到这边是1、2、1、2、2、1，好，都是靠这边我们排列出来的。好，这是它所有可能的状态。好的，那接下来我们想要知道的事情是，这个系统它有可能的能量是多少？能量是多少？就是有可能能量是多少？就是你每次观察这个东西，这个材料有可能的它的能量是多少？那要怎么算？当然啦，我们就去看，我们就可以用 ensemble average 的方式的概念去说 ，OK， 我现在有25个25个这个东西，它有可能是 A， 有可能是 B， 有可能是 C， 有25个。它在这个时间点，它可能是11，它另外一个可能是23，另外可能是12，不不不，就算出来啊，就应该说量测出来哈，在 time t 里面我们就量测出来这个东西。好，这个东西呢，如果今天 A 的话，当然就是 1A 了，这样子11的状态量出来的它的能量就是 1A，那 N 的话也 1N，那它量出来的能量就是这个能量。OK， 那它总能量会是多少？你预期看不是总能量，你预期你从这边找到一个随便挑一个状态，你觉得它会是什么样的能量状态？当然是期望值嘛，对不对哈？所以你就把 Pi 它的几率乘上它的能量，全部加总起来，会得到它的 E bar。这个东西 E bar 就是 ensemble average 的能量状态。好，那其实我们就这样子就可以算出，然后这个能量状态基本上就是我们的 long time average 的实验量测出来的。OK， 那这时候其实啊，这一个地方根本就不需要写在上面。那为什么要写呢？我只是要解释给大家听，为什么是 time t 不是 time plan t plan， 没差的原因是因为，即便你把这个东西变成 time t plan 了。然后它里面都改了，对对对 ，A 是改了没错啊，1.1，2.2，对，它的确改了，但是它的分布几率分布是不会改的。你看到这边两个一，这边也是两个一，虽然是不同的 ensemble 的成员，但是它都是就是分布都一样，而且它算出来的 E bar 也会是一样的。OK， 所以说这2种都是对我们来说都是一样的 ensemble 的 average 的方法。那当然你可以说，哎，25个你随便拿出来都会是E bar吗？哎，当然不会啊。但是如果你今天是10的25次方个，10的25次方个，那这样子你每次拿出来的东西都会是一样的哦。基本上你很难遇到不一样的。OK， 大概是这个样子。Now, the canonical ensemble average, ensemble, example 2. We're kind of using, I mean, this example 1, example 2 is actually very similar, but just using different story, different analog, 不一样的类比，但基本上就讲一样的事情。All right, so let's talk about the very large water cooler. Okay, imagine that you have a really big water cooler, and the water cooler has many bottles. The bottle containing 10 to 25 molecular N, okay, and volume is 33 ml. Okay, and with N molecule interact inside this bottle. And this bottle, many bottles, you can imagine that this is kind of ensemble member, all right, just like A and B and C in the previous page. So, again, this is MBT, right? Because you have a water cooler. So now, every bottle has EI, right? EI, every bottle has EI. And it is defined by the N and V, right? N and V. And T is always the same, so it's not defined. So NV. Okay. Allowed set of energy. All right. So there are many energy. E, A, E, B, E, C, E, H, blah, 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 blah. All right. So now the key question is that what is the probability that your water will be in state I with energy EI? What does that mean? Which means that we are going to determine this. Okay, PI here. We want to find what's the probability for EI energy. Yeah, so if we can determine PI for EI, we can determine ensemble energy, right? Ensemble average energy. So this is the key questions. We want to find each probability for each energy state, each possible energy state. Okay, this is the question. 好，接下来我们要讲的是第二个例子。第二个例子我觉得比较平易近人哈。那你可以想象一下，就是你有一个瓶子，瓶子里面有10的25次方颗在里面，然后它的体积是330 ml， 然后呢，它已经被定住了嘛，然后你放到这样的温度，冷水浴或冰水浴随便了哈，这样酒瓶好了，酒瓶放在维持温度的一个容器里面，然后呢，我们现在就可以看到，其实这一个小瓶子就好像我们刚刚讲的 A 系中成员 A 系中成员 B、C、D 这样下去，每一个都有可能自己的能量嘛，对不对哈？那这时候我们有一个重要的问题就是，我想要知道就是几率有几个，怎么讲？假设你拿到一个瓶子，能量是你指定的你指定的几率是多少 ？OK， 假设你指定说，哦，这个能量是3个单位，然后我要去拿出来，哎，也是3个单位，这样几率是多少？那为什么要做这件事情？因为我们的目标是这个啊，E bar ensemble average 嘛，哈，那怎么样得到E bar？期望值嘛，所以我们要得到每一个能量跟它的出现的几率，这样我才可以算得出我拿出一个瓶子，它的能量是我要找的那个能量的几率是多少啊，对不对哈？好 ，next， so let's talk about before we talk about probability, we need to talk about number, right? So we use the number of bottles to find the probability for energy, EI. Okay, so now we say A is the number of the number of bottle has particular energy. Okay, so state J has the energy EJ, and the EJ has there are AJ bottles has EJ energy. Okay, so the ratio of the number is AJ over AK. Okay, the ratio for different state, J state and K state is AJ over AK. Of course, this ratio can be written as a function of EJ and EK. No problem, right? Of course, if you choose EJ, if you choose EK, you can get the total number of AJ and total number of AK, and you do the ratio. So of course, this is a function of EJ, EK. I guess you can understand this, right? Now, key things here, key important things here. This ratio should not depend on the arbitrary choice of 0 for E. What does that mean? Actually, if you have EJ and this is EK energy, okay, and EJ has AJ number. EK has AK number of bottle, right? And you find that actually, let me close it a little bit. Right. Actually, what is the EJ and EK number? The number actually defined by human being. The number is actually defined by human being. Human setting, hey, this is a 0 point. Or, hey, this is a 0 point. Or this, or that, or that. They are all possible. All right? So which means that the value EJ, EK is actually not real factor. A real factor for AJ and AK is actually the difference between EJ, EK. Because 0 point can be changed, but the difference between EJ and EK are not changed due to the define of 0. So our AJ and AK ratio can be written by as a function of the difference between EJ and EK. So now we change this to here. All right. Now, mathematic trick is coming. Consider another system have energy EL, and the ratio between AJ and AL can be written like this. So AJ to AL is J minus EL, no problem. KL is KL, okay? So from here to here, no problem, right? 好，我们现在讲的是，如果我们要知道每一个能量的几率的话，先从要知道每个能量的个数着手。好，那现在呢，我们就说 AJ 就是能量 EJ 的频子有 AJ 个，能量 EK 的频子有 AK 个，那它们之间的比值当然是函数，是 EJ 跟 EK 的函数啊。哦，当然是这样嘛，绝对没错嘛。你指派一个能量，你就有它的数字，所以它们的比值当然是 EJ 跟 EK 的函数。好，那这时候有一个很重要的概念，我也觉得还蛮神的哈，就是其实啊，这个 AJ 跟 AK 的这个比值，它不能是跟EJ 跟 EK 的绝对值来受影响。为什么？因为值这个东西，能量这个数值其实是人类定的。我们人类可以说某个值是0，我也可以说这个值是0，我们可以说这个值是0。重点在于，就是那个值是随便人定的，这个原点是随便人定的。所以说，真正的影响其实不是绝对 EJ 跟 EK 的值，而是 EJ、EK 的差距。这个差距是不会变的，不管你的0在哪里，它的差距是不会变的。所以 AJ 跟 AK 真正的影响的是它们之间的差距。OK， 好，那用了这个东西以后，我们就可以加入另外一个 energy L 来参战啊。那它们之间的 AJ 跟 AL 的比值就会是这个 ，AK 跟 AL 的比值是这个。好，那接下来要怎么做呢 ？So now, if we have the number of state AJ, AL, you see, AJ, AL is actually AJ divided by AK times AK divided by AL. So they can cancel each other, right? So it's AJ divided by AL, no problem. And here is EJ minus EK. Here is AK minus EL, no problem, right? And they need to times together. So you can see that here is EJ minus EL equal to the function of EJ minus EK, EK minus EL. What does that mean? You see, this is X plus Y, and this is X. Sorry, this is X, this is Y. So X plus Y, X and this is y. Okay, you find this function is x plus y equal to fx fy. Oh, it is exponential. AI must be exponential shape. Looks like exponential. All right, I will finish. Oh, sorry, I won't finish this. You will see me finish it in the video. All right, and I will see you on what? Sorry, I will see you on 12th of November. All right, you will have the exam next week. All right. Good luck. Thank you. 就没办法完成这个哈，要用 video 完成了哈，不好意思。好，谢谢。